Hello everyone. Welcome to this video. Today, I'm excited to share our recent work on improving object detection in remote sensing images under sparse annotations. This is a challenging but critical task for applications like urban planning, environmental monitoring, and defense systems. In remote sensing, object detection is difficult due to dense object distributions, varying orientations, and severe class imbalances. Traditional methods require fully labeled datasets, which are expensive and time-consuming to create. To reduce annotation cost, researchers have explored sparsely annotated object, where only a small fraction of objects in each image are labeled. However, existing methods struggle with unreliable pseudo-labels and confidence misalignment, especially for rare classes. Current pseudo-labeling methods often rely on confidence scores to select foreground pixels. But we found a serious issue. Underrepresented classes sometimes have high confidence, while common classes may have low confidence. This mismatch misguides the model and hurts performance. To solve this, we turn to large language models not for language, but for their strong semantic reasoning ability. We use them to generate high-quality class prompts that guide the pseudo-labeling process, making it more semantically aware and reliable. Our framework is built on a multi-branch input architecture, which seamlessly integrates both supervised and unsupervised learning pathways. This allows us to leverage both sparse annotations and unlabeled data effectively. In the supervised branch, we tackle a key challenge: hard negatives. These are background pixels that look like objects and confuse the model. Our AHR module dynamically adjusts the loss contribution of these negative samples based on their confidence scores. It reduces the weight of high-confidence negatives that are likely wrong, and preserves useful background signals. This leads to more stable training and better convergence, especially under sparse labels. In the unsupervised branch, we introduce the LSP module. Here, we use Vicuna v1.5 to generate class-specific prompts for each image. We feed the image in a text query like, choose categories in the image, into the LLM. The model then predicts which object categories are present. For images with some labels, we combine LLM predictions with existing annotations to boost accuracy. This provides semantic guidance that is especially helpful for rare or confusing classes. With the class prompts from LSP, the CLA module selects high-quality pixels for pseudo-labeling. It uses a three-stage process. First, it keeps pixels that match the LLM-generated class prompt. Then, it selects top confidence pixels globally and per category. Finally, it merges these with any available ground truth pixels. This ensures balanced and semantically meaningful pseudo-labels, reducing bias toward frequent classes. The MBI structure ties everything together. It allows the supervised and unsupervised branches to co-train and reinforce each other. The teacher model generates pseudo-labels guided by LLM semantics, while the student model learns from both sparse labels and refined pseudo-labels. This cyclic process continuously improves detection quality. Together, these modules form a robust and self-correcting system that significantly improves pseudo-label quality and detection accuracy, especially under very sparse annotations. To validate our method, we conducted extensive experiments on two challenging remote sensing datasets, DOTA and HRSC 2016. Let me walk you through some of the key results that demonstrate the effectiveness of our approach. Table 1 shows the performance comparison on the DOTA dataset under different annotation rates, from just 1% to 10% of labels. The first block shows fully supervised baselines. You can see that their performance drops significantly as the annotation rate decreases. The second block contains semi-supervised methods like unbiased teacher and dense teacher. While they help, they still struggle with the unique challenges of aerial images. The third block is where sparsely annotated methods like PECL and ours are listed. Our method consistently outperforms all others across every annotation rate. For example, with only 5% of the labels, we achieve 63.95% map, which is a huge 13.13% absolute improvement over dense teacher. Table 3 answers a very important question: which LLM should we use for this task? We tested several popular vision language models like LLVA, Phi 3.5 Vision, and in turn VL2. The metrics we care about are the accuracy of the class prompts they generate and their computational cost. You can see that while other models are faster, they make many more mistakes. Our chosen model, which is based on a Vicuna backbone adapted for remote sensing, strikes the best balance. It achieves the highest number of correct predictions with a reasonable latency. This proves that task-specific adaptation is crucial. Table 4 is a brief ablation on the design of the textual prompt we feed to the LLM. Through careful experimentation, we found that the specific wording of the instruction significantly impacts the LLM's reasoning ability. This might seem like a small detail, but it highlights the importance of designing precise instructions to get the most out of these powerful foundation models. Finally, Table 6 is our ablation study, which proves that every part of our framework is essential. The baseline is just a standard detector trained on sparse labels. Its performance is very low. When we add just the AHR module, we see a massive jump in performance. This shows that handling hard negatives is perhaps the most critical step. Adding the LSP and CLA modules gives another significant boost. This proves the value of using the LLM for semantic guidance and smarter label assignment. Finally, the full model with the MBI architecture achieves the best results, confirming that the synergistic integration of all components is what delivers the winning performance. In the future, we plan to extend this framework to other types of sparse annotations and explore its applicability to video object detection. We also aim to integrate more efficient LLMs to reduce computational cost while maintaining performance. If you're interested in the details, check out our paper and the code on GitHub. Thanks for watching.